So in section 4.7, we were talking about how to find a power series that could represent a given function that we might be interested in. And what we did was we leveraged our knowledge about the geometric series. We said, well, I know that the geometric series with the ratio r sums to 1 over 1 minus r. So it must be that the function 1 over 1 minus x must be equal to this infinitely long polynomial 1 plus x squared plus x cubed. So we had an infinitely long polynomial that converged to this rational function 1 over 1 minus x. And we were able to extend that. We were able to leverage that to come up with some other nice functions. So for instance, 1 over 1 plus x squared was sort of closely related to this geometric formulation, and we were able to come up with the series 1 minus x squared plus x to the fourth minus x to the sixth, and so on, that would converge to this function 1 over 1 plus x squared. And we were even able to say something by integrating this function. See, this function 1 over 1 plus x squared integrates to our best friend, the arctangent function. So we just went through integrating this polynomial, this infinitely long polynomial, term by term, and we were able to come up with a series expansion for the arctangent function. So what hopefully this piques in your mind is a curiosity about what kinds of functions we can come up with a series approximation for. Are we limited to functions that are related to this geometric kind of formulation? Or can I find a power series expansion for any function I like? I found one for arctangent. What about other trig type functions? Could I find one for sine of x? For cosine of x? Well, we know sine and cosine are closely related to the exponential function by Euler's formula. So what about e to the x? If I gave you any function willy-nilly, is there a polynomial, an infinite polynomial that I can fit to this function? And that's what we're going to talk about in this section, section 4.8, which is our last section. So let me give this a name, section 4.8 is Taylor and Maclaurin series. And the idea starts by going back to something that we understand well, which is the tangent line problem. The tangent line was a major focus of our study in Calculus 1, and we said if I have some function f, and for instance, I know some information about f at this point. Let's start at 0. We'll start at 0, at the x value 0. So if I know that f of 0 is b, and I know that f prime of 0 is m, then I can draw a tangent line. Maybe I name it L of x, and the tangent line L of x, mx plus b, will have the property that L of 0 equals b, which is exactly f of 0, and L prime of 0, if you look at the derivative of my tangent line, the derivative of my tangent line is exactly m, its slope, and that's exactly equal to f prime of 0. So, I mean, if you think about a tangent line, exactly what a tangent line is it's a first-order polynomial. It's a first-order polynomial that I fit to my function f such that the value of the polynomial at the point of tangency matches, and the slope of the polynomial matches the function at the point of tangency. If we were to zoom in so close on this blue function that it looked like a line, the line that it would look like is exactly L, the line of slope m and with intercept b, y-intercept b. So the fundamental motivating question behind the idea of a Taylor or a Maclaurin series is to say, Question. If a tangent line is just a first order polynomial that matches value and slope of f at one specific point, can we find a tangent parabola? A tangent cubic? If I am finding this tangent line was just fitting a first order polynomial that matches the value of f at 0 and matches the slope of f at 0, why stop there? I could create another polynomial, a parabola, a quadratic polynomial that matches f not only in value, not only in slope, but also in concavity at that one point. So let's bring this down here. And now what we'll think about is, how could I fit a tangent parabola? That's not very pretty, is it? Let's try that again. So here's a quadratic function. Let me call it p of x. And p of x is it's a quadratic function. It's a parabolic function. So let me call it ax squared plus bx plus c. And the goal will be to pick a, b, and c such that p matches f at x equals 0 up to the second derivative. i.e., I am going to pick a, b, and c such that p of 0 equals f of 0, p prime of 0 equals f of 0, f prime of 0, sorry, and p double prime of 0 matches f double prime of 0. Notice this problem is not that much harder than the tangent line problem. The tangent line problem, we said, I know the slope of f, and I know the slope of f, and I know the value of f. I'm going to fit a first order polynomial that shares both that value and that slope at 0. Well, now we're going to do the exact same thing. We're going to find a parabola that matches the value, the slope, and the concavity of f at 0. So what should we do? We should say, well, p of 0, going back to the fact that p of x is ax squared plus bx plus c, p of 0 is exactly c. P prime of 0, if I look at p prime of 0, well, p prime is going to be 2ax plus b, and I'm going to evaluate this at x equals 0, and that gets me exactly b. P double prime of 0 is, let's see, the second derivative of this parabola is 2a. So 2a, that doesn't depend on x anymore. This, that is the second derivative. That is the 2a is the second derivative of this parabolic function. And what do I want? I want p0 to equal f of 0. So I'll take my function f, and I'll evaluate it at 0. And that's going to be how I find my value of c. Next, I need p prime to match f prime of 0. So what am I going to do? I'm going to take b and I'm going to set it equal to f prime of 0. Remember, f prime is the function we have our hands on. F prime is the function we're trying to approximate, so we're allowed to ask any questions about f that we want. Lastly, I want p double prime of 0 to match f double prime of 0, so I'll set 2a equal to f double prime of 0. Or really what I should say is that a is f double prime over 2. So filling these in to our polynomial, I have p of x equals the quadratic term f double prime of 0 over 2 plus the x squared plus f prime of 0 x plus f of 0. And now this is a parabola. This is my parabola that matches a parabola that matches f's value, slope, and concavity, all at x equals 0. Now we could keep going. What I hope is obvious is if we can create a tangent line and we can create a tangent parabola, then we can create a tangent polynomial of any degree we want. So the big idea would be I want to construct an infinitely long polynomial such that p of 0 equals f of 0, p prime of 0 equals f prime of 0, p double prime of 0 equals f double prime of 0, p triple prime of 0 equals f triple prime of 0, and so on ad infinitum. I want to create an infinitely long polynomial, and because it's infinitely long,